Chapter 1, Part 2. The scientific method has several steps. This is the process that humans have invented that helps us in a methodical way address questions about the natural world. That is what the scientific method is. It's a process, and it helps us understand the natural world. We can't answer questions about the supernatural with the scientific method. It is not perfect because it is done by people, and people are not perfect, but it is our attempt to be as perfect as possible in the way that we explore the world and the way that we use our ability to explore it to understand what's happening in it. It doesn't always follow exactly these steps in exactly this order every single time, but in general, first we make an observation or observations about something in the natural world. We think about what kind of reason that would be for this observation to have occurred. And the key with the hypothesis that you make about maybe it happened because of this or maybe because of that, you have to be able to test that hypothesis. If your hypothesis is not testable, then you don't have a hypothesis. So you're going to create a hypothesis, and this is the part that most people, most scientists spend the most amount of time doing science is spent on designing and then conducting experiments. The design of your experiment will determine whether you get good quality data or not great quality data, and that will determine whether the work you do is meaningful or not meaningful. So designing your experiment and making sure that you do it well is really important to doing science. Once you design your experiment and then you do the experiments and or make more observations, and you collect some data, and then you analyze that data. And when we're still not done, because now we've got to replicate it. Now we've got to have somebody else replicate the data, somebody else do the same experiment and get similar results. And if we can't find someone who can get similar results doing the same thing, then maybe there's something else going on. So replicability is a really important part of the scientific method. If we get enough data from enough different experiments that all support the same kinds of hypothesis over and over and over, and we get no data that refutes the hypothesis, then eventually, maybe, if it's important enough, then this can become a theory. Then your hypothesis may evolve into a theory, which is a funny way of saying it, but it's true. Your hypothesis is going to evolve as you do all of these experiments and repeat them and then modify them a little and tweak them a little this way to find out more and more about the process that you're looking at. Then you may get your hypothesis may eventually turn into a theory. Doing good physiological research means that we have to have quantifiable measurements. We have to have numbers of, it can be blood test data, it could be number of heart attacks or numbers of strokes or numbers of all kinds of terrible things that can happen to people. We have to be able to measure something that we can then do statistical analysis. I'm jumping ahead a little, but we're going to need to be able to do statistics, so we're going to need some numbers. We're also going to need an experimental group and a control group, and for that, what that means really is we're going to have a group that gets the medication, and we're going to have a group that does not get the medication, and nobody will know which group they're in. And by nobody, we mean no patients will know, and none of the doctors or nurses will know either. So the experimental group, if we just have an experimental group and everybody that's in this test, this experiment that we're going to do, I've got a medication and I think that it is going to help reduce the rate of a second heart attack in people who have had one heart attack. And I've done mouse studies, and we'll talk more about the pharmaceutical development process later, but I've done animal studies and I'm ready to test it in humans and see if it works as well in humans as it does in mice. So I get 1,000 people, and I find out about their medical histories, and all of them have had heart attacks, and I give them all the medication, and I wait 5 years, and then I go back to them and I count how many heart attacks did they have after they take the medication. And let's say that after 2 years, 100 of my people have had second heart attacks. Did the medication help? Can we know that? What do we need to know? What do we need in order to know whether the medication helped? What I just described had no control group. It had no group that got no medication. So is 100 heart attacks out of 1,000 people in 2 years? Is that a lot of heart attacks? Or is that a good number? Like, is that lower than what you would normally expect? We don't know that because we didn't have a control group. So when I design my experiment, I have to design a control group. That's a group of people who are medically, age-wise, sex, race, health, general, everything as close to similar in the groups as possible. And one group, the control group, gets no medication, but they don't know it. And the other group does get the medication, and they don't know it either. And then we watch over time. And so at the end of this time, so my experimental group, I said I got 100 people had heart attacks. So is my medication helping? Well, when we look over at the control group, let's say that the control group had 200 heart attacks. Well, that means that my medication reduced the rate of heart attacks, second heart attack, by half, right? We only had 100 heart attacks in the same amount of time. So that's fantastic, right? That's fantastic. But what if we go back and we look at, and we say, well, actually in the control group, they got 98 heart attacks. So now it either didn't help at all, or it actually caused 2 extra heart attacks. So this is why a control group is super important. You've got to have a control group. And often when we do these kinds of things also, we'll have more than one really experimental group. We'll have a low dose, medium dose, high dose, for example. And then we'll compare each of those with each other and with the control groups to see what is better. We're going to have to do a lot of statistical analysis because we're going to have hundreds or thousands or tens of thousands of people involved in these studies, and to find out whether a medication is helping or not is going to require a lot of statistics. And then we're going to write up our information on our study, and we're going to send it to a publication, and that publication is going to be a peer-reviewed journal, and they're going to send, what that means is they're going to send it to somebody else who studies second heart attacks, and who also is interested in that same problem, and they're going to look at what you've written, and they're going to say, well, I think you might have been able to do this a little differently, or maybe next time you're going to try it to do this way, or how can you explain this data, or why did you take out these individuals partway through the study, why didn't they continue the study? So they're going to be, because what the peer review is when you are doing this kind of research, there are literally only a few other people on the planet who know what you study as well as you do. And so those are the only people who can really look at your data and say, yeah, you know what? That's a good study. And no study is perfect. But you can see a good study and you can see a not great study, and every study has some flaws. Every study has difficulties. Every study would like to have a bigger sample size so that their statistics are better. But there's a big difference between a great study and a good study, or a good study and a not good study. And the peers are going to be the ones who can tell the difference, and really nobody else can. And that's why peer review is so important.